Okay, hello everybody. Welcome to lecture 22. This is our final lecture of kind of new curriculum content as such. We have one more lecture tomorrow on Thursday, lecture 23, and that one we will use for just a little bit of advice and I suppose preparation for the exam. And if anybody has a question or anything that they would like to include in tomorrow's sort of review session or exam preparation session, please just let me know by email if you have a chance today. What I'm planning to do, if nobody has sort of any major alternative suggestions, is just to first of all, give some general advice about the exam, which you probably already kind of have, but I'll recall it, and then maybe look at a few sample problems. And maybe tomorrow, so I have a sort of set of sample calculus exam questions for tomorrow. I'll comment on sort of general gist and flavour and style tomorrow. And maybe tomorrow what we'll do is we'll have a look at, in particular, at sample questions 1 and 3 related to chapters 1 and 3 of the lecture notes, since we already had a lecture back in week 9 on an exam type question for chapter 2. But if we don't get through everything tomorrow, I can post some additional updates after that. So that's the plan tomorrow. I mean, I will have some fairly clear, I hope, advice about the exam. And if anyone has specific questions that isn't answered in that advice, please do just ask. And I'm quite happy to try to answer any questions you might have. Okay, either about any specific sort of old questions or about sort of format or, expectations or anything like that. Okay, that's the plan for tomorrow, which is really a review and look ahead to the exam. Our business for today is to finish off chapter 3 of our lecture notes, which is Introduction to Power Series. So in chapter 3, which has been, the theme has been sequences and convergence. So let's just have a quick sort of look back at what we've been doing and where we are. So I think this chapter 3, it's sort of, it's a, I suppose it builds on the previous 2 chapters in a sense, although it doesn't have as much directly to do with integration as it has to do with the content of chapter 2, but it's been about the concept of convergence really in particular. So it had 4 sections. The first part of section 3 of chapter 3 was just to look at some examples, really, examples of infinite sequences, infinite series, and also these power series that we're going to meet properly today. In section 3.2, which was mostly kind of theoretical machinery, we introduced the concept and definition of convergence for a sequence. And that is probably like the most important thing in this chapter in terms of a sort of piece of mathematical machinery that powers a great deal of activity. Okay, but it was certainly a conceptual piece of work regarding sequences and the notion of convergence. So in section 3.3, which was mainly the content of last Thursday's lecture, we talked about infinite sums and how we can sort of use the notion of convergence for a sequence to define what it would mean for an infinite sum of numbers to have the possibility to be added together to produce a numerical result for their sum, for their total. And we're going to build on that a bit more today with this sort of next step in that whole development, which is this concept of a power series. And so, so last Thursday we saw, I suppose, just to summarize very roughly, that sometimes it makes sense to talk about the sum of all the terms in a sequence. And sometimes you can even give that thing a numerical value. So for example, we talked about geometric series, things like 1 plus a half plus a quarter plus an eighth and so on. That sometimes these things do actually have a sum that you can write down that is actually a numerical value. And sometimes that can be useful as well. For instance, if you want to know a good decimal approximation to some irrational number like maybe pi or something, and maybe you can get an infinite series whose sum is actually some number that you want to get at that you can't get at by direct ways and whose value you want to know. So that has a practical use. Today is another sort of step in that development, which is if you have some function and you want to evaluate it, and maybe you have a very good definition for the function, maybe you even know a lot about how it behaves, for example, in calculus, but maybe you can't actually calculate its value at certain points. So here, think about trigonometric functions. Is there some way that this notion about being able to calculate infinite sums can help? And the answer is yes. It's used all the time, even though it's often under the hood and in the background and not directly in our line of vision. But it will be more for you if you're mathematicians or students of mathematics. But these are kind of powerful ideas that really kind of that are used throughout really any area that deals with numbers, although not always in the forefront. So that's our goal. So if you don't know what a power series is, you are about to know. So power series is what we're going to be talking about today. So series means infinite sum. As we've seen that. And power means basically talking about powers, like powers of x, powers of some variable. And so a power series combines those 2 words, powers of some variable, and series infinite sum. And basically, I think a good way to think about a power series is that it's like a polynomial, but with infinitely many terms. So we all know and hopefully love polynomials. They're beautiful functions to work with. They're very nice. Polynomials obviously are expressions, algebraic expressions or functions, which have like maybe a constant term, an x squared term, and a finite number of terms, each of which is a power of x with some coefficient. And polynomials are really useful because they behave really nicely in calculus. You can always integrate them and differentiate them without any problems, and also because they approximate general functions to a high degree of precision. So they're nice things in calculus. They're nice in algebra too, but of course polynomial equations are not necessarily easy to solve. That's another whole subject in its own right. So a power series basically is what you would get if you suspended the sort of rule that polynomials can only have finitely many non-zero coefficients, and if you allowed them to have infinitely many non-zero coefficients. Okay, so what you get would be sort of like a polynomial with infinitely many terms. Whether such things make sense or not is a question to be considered, but certainly you could talk about them. You can write them down as kind of formal objects. So this is what a power series looks like. It's something like a0, a constant term, so this would be a real number. It could be a complex number in some applications, but for us it's a real number. There'd be a term involving a power of x with some coefficient a1, a power of x squared with some coefficient a2, and so on, a3, x cubed, a4, x to the fourth, and so on. So some of these a's could be 0. Infinitely many of them could even be 0. So, a polynomial would be a power series in which all but finitely many of the coefficients are 0. But power series are more extensive than polynomials because power series can have infinitely many non-zero coefficients. So that's what a power series looks like. So for example, if all the a's were 1, an explicit example would be 1 plus x squared plus x cubed. Whatever, you could put whatever you want as the coefficients, but if they were all 1, that's what your series would look like. So this would be the sum from 0 to infinity of just x to the I with the coefficients all equal to 1. Okay, so in general, of course, we can write it this way. Okay, fine, we can do that, sure, no problem. Oh, sorry, I just written down the example. It's written below there. We could do it, but what does it mean? Why would we do it? Is this just kind of a kind of instrumental extension of the concept of a polynomial just because we can, or does it have some value? Can we make sense of it in some way? And I suppose, there are lots of ways to think about polynomials, and I know you've already studied polynomials in this year, and at least two different ways. Like in calculus, we tend to think about polynomials as being functions, and we draw their graphs, and we think about their maximum and minimums, their maxima and minima, and their roots, and so on. In algebra, and I know you've been studying this with Dane, you tend to think of polynomials as being sort of formal expressions, and maybe you care about whether you can factorize them, and whether they're irreducible, and whether they have roots and everything. And so there are different ways to think about polynomials. But certainly in the typical calculus viewpoint, we often think about polynomials as being functions that you could evaluate them at different points for different values of x. They have some continuous domain, the real numbers or whatever. You can draw their graph. You can look at the objects that are of interest in calculus, like their extreme points and their critical points, etc. So power series resemble polynomials, at least in a superficial way. Question: can we think of a power series as a function of x? And what does that even mean? Well, I suppose it means, what happens if we plug in? If instead of writing x, this sort of formal abstract variable, you put a number in there instead of x. So what happens if we plug in values for x? So for example, put x equal to 1 or put x equal to 1/2 or whatever in a power series. So what you get then is not a power series anymore. It's a infinite series like we had last week. It's an infinite sum of numbers. And okay, so we have a whole theory developed last week about whether such a thing is itself a number or not. And of course, that amounts to the question of whether the series you have is convergent or not. And we have ways of at least understanding what that would mean, whether or not we can necessarily decide it for every particular example. So can we think of a power series as a function of x? So I suppose we have to ask ourselves, again, sort of superficially, like a polynomial, it sort of resembles a function of x, maybe. But if we want to know the answer to that question, we have to ask ourselves, well, what would happen for a given example if you start plugging in different values of x? Can you actually evaluate this power series for a particular value of x and get a number as the value of some function at that particular x? So that's a kind of a tall order, but we can at least look at it. We can sort of at least wave our hands at it. But this is a very initial introduction to power series. Again, like every other lecture we've had, basically people spend their lives thinking about these questions, and one certainly can. Okay, so here's an example. So, you know, and hopefully at least to indicate what I mean by saying, can we think of a power series as a function? So if we define a function, this function is going to be quoted there because, you know, is this thing actually a function or not? Let's find out. So f of x we're writing as this power series in which the coefficients are all equal to 1. So f of x is 1 plus x squared plus dot, dot, dot. And I suppose it's the dot, dot, dot here that raises the question about whether this thing is a function or not. If it cut off after x squared or after x to the 10 or after x to the 20, there'd be no problem. You can certainly evaluate such an expression, in fact, for any real value of x. But the fact that it goes on forever is what makes it sort of questionable whether this is a reasonable definition. So if you're going to call this thing a function, you know, what would its domain be? How would we, what would its values be at any points in its domain? So, okay, if it's a function, we should be able to like evaluate it. So if, for example, we try to evaluate it at x equals 2, fine, do the usual thing, replace x with 2 in the definition of the function, and that would say, well, f of 2 should be the sum of all the powers of 2 from the 0th power onwards. 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 2 squared, etc. So we get 1 plus 2 squared plus 2 cubed, and so on. So that's pretty hopeless. That is not a convergent series. It's a sum of terms that are growing really fast as we continue along the expression. So that thing is definitely not a number. Whatever else, you know, it's just not. It's 1 plus 2 squared plus 2 cubed. It blows up to infinity. Okay, so you know, we can't. If this is a function, then 2 is not in it. 2 is not in its domain because we cannot evaluate that f at 2. F of 2 is some kind of sum that certainly blows up to infinity. So, okay, so I suppose we can make that remark that if f is a function, if that notion has any reasonable meaning at all, then we can certainly say that 2 is not in its domain. Because if it was, then the function would have to have a value at 2, which would mean we would have to be able to make some kind of sense of this infinite sum of all the powers of 2. Okay, fine. Well, it might still be a function. It just doesn't have 2 in its domain. Let's not rule out that possibility. Okay, if you try to evaluate it at 0, maybe we should have started there. You have some better luck. So if you try evaluating this function at 0, well, that's a lot easier, because when you put 0 in there instead of x, then all the terms except the first one just evaluate to 0. So you just get 1 plus a bunch of zeros, and that's okay. That's 1. Okay, so certainly it does make sense to evaluate this function at 0, and we could say that f of 0, at least, is equal to 1, which is just the constant term here, because all the other ones drop out when x equals 0. All the other ones are 0 except the constant one. So, and certainly that's not a special feature of this particular power series. It's true for any power series that if you put x equal to 0, you get just the first constant term, and all the other terms have an x in them, so they would all evaluate to 0. Okay, great, fine. So what we've discovered about this function so far, if it is a function, is that it has the value 1 at 0, and it doesn't have a value at 2, so 2 is not in its domain. Great. This is a lot of fuss about not very much, maybe. But what else can we do? Well, let's keep going. Let's try a few more things. So, anybody have a question at the moment or a comment? So I suppose the context so far, to be fair, is I've just introduced this thing out of the blue, this infinite sum of powers of x, and now I'm trying to evaluate it at various points. So you might well be asking, well, why would you bother doing that? Why would you bother introducing this thing out of the blue and trying to evaluate it at various points? So I suppose the answer to that, if you're wondering that, is coming a little later today. So try to suspend your skepticism for a few minutes if you are in doubt about that. Okay, but let's stick with this example for a little longer. Okay, so if we try evaluating the same thing, so there it is in the banner there on this slide, at x equals 1/2, then you get something maybe a bit more interesting. So again, taking this to be the definition of f, what's written in the banner there, putting x equal to 1/2, you get the sum of all the powers of 1/2. So that's 1 when n is 0, 1/2, 1/2 squared, 1/2 cubed, and so on. And we can certainly notice, I'll fill in a couple more terms here, 1/2 cubed, 1/2 to the 4. We can certainly say, well, yeah, okay, that's something that we might recognize. I mean, the version for 2 is something that we might recognize as well, but we could see it just growing without bound. Here, the numbers in this sum are not growing without bound. They're shrinking towards 0. You know, we've got 1, 1/2, 1/4, 1/8, 1/16, and so on. So this thing has a chance of being finite because the things that are being added on at each step are shrinking towards 0. And indeed, we might recognize, if you've already had a chance to go through last Thursday's lecture notes in detail, you'll have a chat, you might have recognized this already. If you haven't, don't worry. But this is a geometric series whose first term is 1 and whose common ratio is a half. Every term is obtained from the previous one by multiplying by a half. And we know from last week that a geometric series whose common ratio is less than 1 in absolute value does converge. And not only that, but we can say what it converges to. So if the absolute value of the common ratio is less than 1, and what that means, of course, is that, when every term is obtained from the previous one by multiplying by this common ratio. So basically, if you have the 10th term maybe is obtained from the first one by multiplying by the 10th power of the common ratio. So if the powers of the common ratio are heading towards 0, then at least we can say the series has a chance of not growing to infinity, because of the terms that we're adding on at each step are shrinking towards 0. And that's really what the significance here of the common ratio shrinking, or being less than 1 in absolute value is, that ensures that at least that the terms in the series are heading towards 0. So there's some possibility that the sum might be contained and not blowing up to infinity. Okay, but we did indeed see last week that in such a case, where the common ratio is less than 1 in absolute value, the common ratio is what you multiply by to get from one term to the next. So in this example, it's 1/2. So the series with common ratio less than 1 in absolute value converges to the number given by its initial term divided by 1 minus this common ratio. And in this particular example, where we're trying to evaluate our function f at 1/2, we get this infinite series with initial term 1, common ratio 1/2. The initial term 1 is the constant term in the power series. And the common ratio 1/2, it's kind of worth noting too where that comes from here in this context. The common ratio 1/2 is the x that we're choosing to evaluate our function at. So the x there, x being equal to 1/2 gives us the 1/2 as the common ratio for the particular instance where we're trying to evaluate this function at 1/2. Okay, so and anyway, we can say, okay, if we believe this geometric series business, that the value of f at 1/2 is 2. So okay, great, that's progress, kind of. We can say we can evaluate this function at 1/2 as well as at 0. So that's at least 2 points where we can evaluate the function. And of course, there was nothing really special about 1/2. We can evaluate the function at any value of x, which is less than 1 in absolute value, by the same idea, because if x is less than 1 in absolute value, or put it this way, if we replace x with any real number that's less than 1 in absolute value, we just get the geometric series whose initial term is 1 and whose common ratio is that particular value that we chose between -1 and 1. Okay, so our geometric series basically converges. The geometric series 1 plus r squared plus r cubed and so on converges provided that the absolute value of the common ratio is less than 1. So in general, in our example, so here it is again. There it is written in one way. Here it is written in its kind of longhand power series description, 1 plus x squared plus. Okay, so the assertion is exactly as we did for 1/2, that we can evaluate the infinite series that we would get by replacing x here with any real number in the range -1 to 1, not including the two extremes, -1 and 1 themselves. For any value of x whose absolute value is less than 1, we get that f of x is a convergent geometric series. And here we can say a little more. We can say with initial term one and common ratio x. We could indeed describe the whole power series that way. And so for a value of x in that range between -1 and 1, we can say that, well, a geometric series with initial term 1 and common ratio x converges to the initial term a over 1 minus the common ratio, which would be x. So basically, this series, 1 plus x squared, etc., for any value of x in the range -1 to 1, that series converges when you replace x with this particular value. And what it converges to is 1 over 1 minus your particular x. So somehow the function defined by this power series is, for those values of x at least, the same function as the function defined by 1 over 1 minus x. And so our conclusion is that for values of x in the interval from -1 to 1, in other words, absolute value less than 1, absolute value of x less than 1, that's so this controls the common ratio, keeps it within the range that will make the series converge. for any value of x in that interval, the infinite power series 1 plus x squared plus x cubed is convergent, and what it converges to is 1 over 1 minus that value. So provided that x is in the region -1 to 1, strictly between -1 and 1, then the value of this power series, the value of this infinite series, is equal to 1 over 1 minus that x. And you can check this out for a few values of x. I mean, we saw it already for when x equals 1/2. We got 1 over 1 minus 1/2. That's obviously 1 over 1/2, so it's 2, which is the sum of 1/2 to the n, as n goes from 0 to infinity, the sum of all the non-negative powers of 1/2. Okay, and so in general, if you put x equal to 1/3 or -1/3 or whatever, put x equal to 1/3, you get 1 over 2/3, that's 3 over 2. That will be the sum of 1/3 of 1 plus 1/3 plus 1/3 squared plus 1/3 cubed, and so on. And if you want to just, if you have a bit of time in your hands, which I know you don't because you're all under pressure with lots of things, you can sum a few series of this thing for a few terms for x equal to 1/3 or 1/4 or whatever, and just sort of satisfy yourself that, yeah, this does actually work. If you evaluate 1 plus 1/3 plus 1/9 plus 1/27, go a few terms out, you should get the same thing as taking 1 over 1 minus 1/3, which would be 3 over 2. Okay, so this power series, 1 plus x squared, so, we started with this sort of formal expression involving x. What we have kind of established is that in terms of thinking about that being a function, so for any value of x that you'd like to throw into it, you can get an infinite series. The series will be convergent if the value of x that you chose is between -1 and 1 strictly in absolute value. In that case, you get a convergent geometric series. And for those values, for each such value x, this infinite sum is 1 over 1 minus x. So we can say that this is what they call a power series representation of that expression or function, 1 over 1 minus x. It applies for values of x in the interval -1 to 1. That's called the interval of convergence of the power series. And 1, which is like the radius of that interval about its center, which is 0, is the radius of convergence. Okay. And we say that the power series representation of the function f of x equals 1 over 1 minus x is this power series. And that representation applies for values of x in the interval -1 to 1. Okay, so I suppose it's a way of representing a function as an infinite series, and it's certainly an important example. What it's actually good for is open to question, but we'll move on to that in a couple of minutes. And I guess the other question that somebody might ask very reasonably would be, well, what if x is outside of the interval of convergence? Certainly the expression 1 over 1 minus x makes sense for every value of x except for x equals 1. For division by 0, but if x equals 2, for example, then 1 over 1 minus x still is something that you can evaluate. It's just -1, but this thing on the right certainly does not resemble that at all. So basically, for values of x outside the interval of convergence, the function might still make sense. It might still be evaluatable, and it might be perfectly well defined, but the power series just doesn't have any connection to it anymore for values outside that region. At the endpoints of the interval of convergence, sometimes the series might converge and sometimes not. In this particular instance, if you put x equal to 1, the series certainly does not converge. You get an infinite sum of 1s, and the left-hand side doesn't evaluate either because you get 1 over 0. If you put x equal to -1, I guess you get 1/2 on the left, but on the right you get this alternating sum between 1 and -1, 1 minus 1, so it doesn't converge. Okay, so but for values within the interval of convergence, strictly between -1 and 1, the series converges, and what it converges to for each such value x is 1 over 1 minus x. Okay, that's our first example of a power series representation, and really it's sort of classic geometric series representation. I have a few more comments about it, but does anybody have a question or a comment first? Okay, well, let me say 1 or 2 more things about that. So I suppose, fine. I suppose the point of this example really is to kind of show that, yeah, sometimes something that has a sort of closed form expression involving x, like this 1 over 1 minus x, can also have an infinite series representation. It might not apply for every value in the domain, but it applies for some of them. And so that's already kind of a curious thing, I suppose, you know, that this expression 1 over 1 minus x, which is a nice rational function of x, could actually be, at least on some domain, somehow we can regard it as being the same thing as this kind of infinite polynomial, this power series, 1 plus x squared, etc. So that's a curiosity, if nothing else. I guess a remark about it is, you know, I promised we'd have something useful here. We don't really yet in terms of immediate practical application, because you know, this power series representation is not really particularly useful if what you want to do is calculate 1 over 1 minus x for a particular value of x, because you can do it directly. You can just, you know, you can put your x into that, into 1 over 1 minus x and do it directly without so much fuss about infinite sums. So I'm not really trying to sell this as something that has immediate practical usefulness, this particular example. But if you could have a power series representation for a function like sine of x and use it to evaluate, or at least to approximate, the value of sine of 1 or sine of 9 or sine of 20, that might have some practical use, because we often have occasion to want to know what the sine of something is, even, you know, in some, maybe in some geometric construction or in some application or whatever. So, and these numbers, sine of 1 or sine of 9 or sine of 20, I know I keep saying this, but let me say it one more time. You know, what does it mean? What does sine of 20 mean? Okay, and I know we're all, at least many of us, from our experience, are very used to thinking about sines and cosines in terms of triangles, but sine of 20 doesn't really have anything to do with triangles directly. Like, sine is a function of numbers, not of angles. And the sine of the number 20 is the y-coordinate of the point that you reach by traveling a distance of 20 anti-clockwise around the unit circle, starting at the point 1, 0. Okay, that's what it is. And so it has this clear description, but that doesn't tell us anything about what its value is, apart from the fact that it's between -1 and 1. A distance of 20 is roughly sort of 3 laps of the unit circle plus a bit, because the circumference of the unit circle is a bit more than 6. But okay, so you know, where are we after traveling a distance of 20? What's their y-coordinate? We can't really say it immediately. But so, of course, you can ask your calculator, or you can consult some oracle, such as a calculator or a piece of software or a table in some old book, if you want to know what the sine of 20 is. But which is fine, of course. But you know, how does the calculator do it? And the answer, of course, is it uses some series representation of the sine function. It doesn't try to sort of do it in a geometric way by looking at the unit circle. Okay, so questions in general, and these questions, you know, would fill a library. They have filled libraries. So we're not going to answer them in the next 20 minutes. But what kind of functions can be represented by power series? On what sorts of intervals or subsets of the real numbers? And I suppose more practically, if a function could be represented by a power series, well, okay, how would you know? We're not going to really tackle that one so much, but we will look at the second one. How would we come up with such a series? How would we find its coefficients? And you know, it seems like a kind of magical thing to me that, you know, you have some function like the sine function. Okay, theoretically, maybe you have some machinery that tells you it has a power series representation, but how do you actually go and find the coefficients in that power series representation? You know, what possible equipment could we have for this? And the answer, curiously, is that we have it all for at least for some functions, and we'll see how. So the rest of this lecture, which is also the rest of the lecture content for the course, will be taken up with an example to try to demonstrate how we can actually calculate the coefficients in the series, provided our function is sort of reasonably nice and we know enough about it. And basically what we need it to satisfy is we need to be able to differentiate it, which is no problem for trigonometric functions. And we need to be able to evaluate it at least at 1.0, for instance. And if we can do those two things for the function and its derivatives, we are actually in good shape for writing down a power series representation. So let's see how it goes. Okay, so the last item here is a technique which sometimes works for lots of nice functions for writing down a power series representation, and it's called the Maclaurin series expansion. So anyone have a comment or question at this moment? Okay, if not, then let us proceed to what is really the last thing. So topic here is Maclaurin series or Taylor series. Okay, so you may well have come across either of these terms before. The Maclaurin series, which is the one we're going to talk about, is a special case of the Taylor series, which is a hugely important thing in all manner of theoretical and applied contexts. Okay, so suppose that f of x is a function. Okay, so, and I mean, it's the kind of function that we meet in calculus, and I want it to have the property of being infinitely differentiable. So that means that all of the f of x has a derivative, and that all the derivatives of f are themselves differentiable. So you can, in principle, keep differentiating it, and you never run into trouble. Okay, so something like a polynomial function would certainly meet this criterion, although they're not interesting because there already are power series. Something like a trigonometric function, sine or cosine, certainly meets this criterion. Something like an exponential function certainly does. Okay, so we want a function which is differentiable repeatedly on its domain. Okay, so and supposing that f is represented by the power series which has coefficients Cn for x to the n. Okay, so and when I say f is represented by the power series, I mean on some interval of convergence at least, maybe not necessarily in the entire domain of f. So we're giving ourselves this kind of hypothesis that f does have a power series representation. Okay, and the question of when that can occur and when it doesn't occur is another sort of huge subject that we won't really go into, but suppose it does. Suppose it has a representation of that type. Okay, and then the assertion is that if we start with the hypothesis that f does have a representation like that, which applies at least in some interval, okay, at some interval that includes the point 0, then we can work out appropriate values for the coefficients using the following idea. So first step, and we applied this already in the previous example. So this is, just in case anyone doesn't like the sigma notation, this is C0, x to the 0, plus C1x plus C2x squared, plus C3x cubed, plus c to the 4, x to the 4th. And the assumption that we're making is that we know what f is. So maybe it's something like sine of x. Think of something like that, or cosine, or the exponential function e to the x. And we would like to know what the coefficients would be that would give us a power series representation. And maybe our motivation might be that we want to know the value of our function at some point. And so we'd like to know what these coefficients are so that we could figure out at least a partial sum of this series, which would give us an approximation to the value of our function at the point of interest. So the strategy for working out appropriate values of the coefficients is first, just put x equal to 0 into both sides here. Okay, so we're imagining that we know what f is, but we don't know what the c's are. Then f of 0, which we suppose we can evaluate, so think about the cosine function or the sine function, we can evaluate its value at 0. That would be c0 plus c1 times 0, plus c2 times 0, plus c3 times 0, and so on. So just the first term survives, and all the other terms, when we put x equal to 0, give us 0. So what we discover is that C0, the constant term in this power series representation, should be the value of f at 0. And maybe, even if we can't evaluate f at every point, we can evaluate it at 0. And that's certainly true for the trigonometric functions. Okay, so C0 would just be the value of f at 0. So we're going to look at an explicit example in a minute where we see how this can work in lots of applications. Okay, to calculate C1, okay, here we can't do it directly, because putting x equals 1 or something like that is not going to help us because we don't know what all the c's are. So we'd have some infinite sum that we know nothing about. But to calculate C1, the trick is to look at the first derivative of f. Okay, so the idea here is f of x is C0 plus C1x plus C2x squared, and so on. Okay, so f dash, the derivative of f at x. So what we're going to do here is this is like a polynomial on the right hand side. Just differentiate it one term at a time. Okay, and the question about whether that's a reasonable thing to do or whether it's a dodgy thing to do is another thing that's dealt with in the whole theory of series. So we won't deal with it here. We'll just do it. But yeah, I suppose this comes with a little bit of a warning that there's a lot of theoretical machinery behind this, behind saying that differentiating f, which is an infinite sum of powers of x, we can just do it by differentiating the terms. But if we do that, we get f dash of x. C0 is a constant, so we get 0 there. C1x, differentiate that, we get C1. C2x squared, differentiate that, we get 2C2x. C3x cubed, differentiate that, we get 3C3x squared, and so on. Okay, so to take f dash of x, the derivative of f, so here's where we need to know that our function is differentiable. Okay, so the series representation of the derivative of f would be this thing. Meanwhile, we have an explicit description of f as sine of x or cosine x or whatever. We can differentiate that directly as well. And we get that f dash of x is c1 plus c2, 2c2x, etc. And then put x equal to 0 in there. Okay, so f dash of 0 would be c1 plus 2c2 times 0 plus 3c3 times 0. So the only term that survives here is the c1 term. And what we say is that c1, we should take it to be the value of the derivative of f at 0. So if we're able to evaluate f at 0, which was this bit, and if we're able to evaluate f dash at 0, which is this bit, then we can fill in the coefficients c0 and c1 here. c2 will come from the second derivative of f, evaluated at 0, and so on. So if we can write down the derivatives of f and evaluate them at 0, we're in business here. We can basically fill in all these coefficients. And the key point is, by taking successive derivatives, you're able to kind of pick out these coefficients one at a time and relate them to values of the derivatives of f at 0. So this was Maclaurin's big idea. Maclaurin was from Scotland, and he was a child prodigy. Went to university in Glasgow at age 14 or something, and spent his career in Aberdeen and Edinburgh, and is most famous for this Maclaurin series, but did many things. This was in the first half of the 18th century, so really quite a while ago, but still has extraordinarily sort of powerful applications. Okay, for the second derivative, C2, the second derivative of f, so again, f of x is C0 plus C1x plus C2x squared plus C3x cubed, etc., and so on. Differentiate that twice. The C0 term falls out the first time you differentiate. The second time you differentiate, you've lost the C1 term as well because it only had an x with it. Differentiate C2x squared twice, you get 2C2x the first time, you get 2C2 the second time. Okay. Differentiate C3x cubed twice, you get 3C3x squared the first time, you get 6C3x the second time. Differentiate C4x the fourth twice, you get 4 times C4x cubed. The first time, you get 4 times 3 times C4x squared the second time. So you can see this kind of pattern developing with the second derivative. Putting x equal to 0 at this point will cause all terms except the C2 term to drop out because you're replacing x with 0 and all these subsequent terms. There's an x there, an x there, an x there. So those will all fall away when you put x equals 0 in the second derivative. And what you find is that the second derivative of f evaluated at 0 is not just C2, but it's 2 times C2 because it's 2 times 1 times C2. So C2 is the second derivative of f evaluated at 0 over 2 times 1, and so on. C3 is the third derivative. So this notation, fk of x, is often used for the kth derivative of f. Of course, you can write dashes. If you have 5 or 6 dashes, it can get a bit difficult to count them. So it's handier to use this k notation sometimes. So C3, the x cubed term in the Maclaurin series, is the value of the third derivative of f at 0 divided by 3 times 2 times 1, which is the coefficient that's multiplying it by the time you've differentiated it 3 times. And that's how it goes. Okay, so we can actually, if we're able to calculate derivatives of f and evaluate them at 0, then we can calculate all of these coefficients. So continuing this process, you don't have to memorize this formula, but it's just, it's the conclusion of that process. The coefficient of the x to the n term in the Maclaurin series representation is nothing but the value of the nth derivative of f at 0 divided by n factorial, which is the product n times n minus 1 down to 1. Okay, so it's really quite a neat thing. If you have a function where you're able to evaluate the function and its derivatives just at the single point 0, then you can write down this Maclaurin series representation. Okay, and again, it's not automatic in advance that the series will represent the function everywhere, but in many cases it actually does, and gives us a way of evaluating functions that we might not be able to evaluate otherwise. So to see a version of this acting in practice, I suppose you might be wondering, well, okay, fine, like this is great, but you've got some function f that's maybe difficult to deal with. How do you, is it a big expectation to say that you want to be able to evaluate f and all its derivatives at 0? Like, is that asking a lot? Well, I suppose it might be, but there are lots of cases where it really isn't, where we do have that information available to us. So here is our last example, power series representation of sine x. So if you take our f of x to be sine of x, and we are kind of giving ourselves the hypothesis that we do have a Maclaurin series that represents sine of x, then the Maclaurin series formula tells us that Cn for a particular n, Cn is the coefficient of x to the n in the series representation, that it should be the nth derivative of f evaluated at 0 divided by n factorial. Okay, so what you have to be able to do if you want to write down these numbers is be able to evaluate derivatives of f at 0. And in the case of sine x, that's pretty easy, really, because not only do we have no problem evaluating sine at 0, but we also have the handy little fact that the derivatives of sine just sort of cycle through sine and cosine, basically, with some minus signs as you proceed. So f of x is sine of x. Okay, f of 0 is sine of 0. That's the y-coordinate of the point 1, 0, so it's 0. F dash of x is cosine of x. F dash of 0 is cosine of 0, which is the x-coordinate of the point 1, 0. That's 1. The second derivative of x is the derivative of cosine x, which is minus sine x. And the second derivative of f at 0 is minus sine of 0, so it's 0. And the third derivative of x is minus cosine x. So the third derivative, so we can call it f brackets 3, or we can call it f with 3 dashes, is minus cosine of 1, so that's minus 1, and so on. So the 2 dashes here is the same thing as writing f with 3 in a bracket. And after the third one, I guess you sort of probably need to use the number because it gets a bit hard to count the dashes. But anyway, that's how it goes. And of course, once we're there, the next derivative after that, the fourth derivative of x, sorry, that's supposed to be a 4. Is a derivative minus cosine x is sine x again. So the derivatives of sine just cycle through sine, cosine, minus cosine. So it's really neat. And and these numbers then just cycle through 0, 1, 0, minus 1. So we find that C0 is 0, that's f of 0. C1 is 1, that's f dash of 0. C2 is f double dash of 0, the value of the second derivative at 0 over 2 factorial. That's 0 over 2 factorial. The coefficient of x cubed is the value of the third derivative at 0, which is minus 1, divided by 3 factorial. So it's minus 1/6. The fourth derivative at 0 is 0. C4 is 0 over 4 factorial. And of course, whenever n is even, then we're dealing with the value of a even derivative of sine at 0. So it's just sine of 0. So the even values of n are all going to have coefficient 0. And the odd values have coefficient basically plus or minus 1 over n factorial, and it alternates between plus 1, plus and minus. Okay, so the power series representation of sine x, basically the pattern continues. If k is even, then the kth derivative of sine x at 0 is sine of 0, so it's 0. So the kth term is 0. If k is odd, then the kth derivative of sine is either cosine or minus cosine, and it alternates. So if k is 1 mod 4, so if k is 1 or 5, then it's cosine of 0, which is 1, and ck in that case is 1 over k factorial. If it's 3 or 7, then it's minus cosine of 0, so it's minus 1, and ck is minus 1 over k factorial. So the Maclaurin series for sine x is given in this way. If you don't like this version, just give yourself a bit of time to make friends with it if you want to, but feel free to just write it this way. So the 0 term, the constant term is 0, which is sine of 0. The x equals 1 term, the n equals 1 term is x, which is the 1, the coefficient here is the derivative of sine evaluated at 0, which is cosine of 0, so that's 1. The x squared term is 0. The x cubed term is minus cosine 0 divided by 3 factorial, and so on. Then it's plus cosine of 0 over 5 factorial x to the 5, and so on. So this is a series, an infinite power series. We can observe that it only involves odd powers of x, and I guess when you think about it, it's not so surprising because the sine function is an odd function. Its value at minus x is the negative of its value at x. And it turns out, and we're not going to prove this fact, that this power series actually converges everywhere. So for every real number x, this series converges to sine of x. And I guess you could say, oh my God, what if x is like some big number? These powers, x cubed, x to the 5th, x to the 7th, and so on, they're blowing up. So, how is the series going to converge? And well, the answer is that the factorials kind of control them. We've got x to the 7, so if x is some high number, x to the 7 is obviously potentially a huge number, but it's sort of controlled by the 7 factorial, and the n factorials grow, and they sort of control the growth. So this series actually converges for every real number x to sine of x, and can be used to evaluate the sine function. So I think it's kind of really remarkable when you think about it. That series, think about plugging values of x in there. The connection to the unit circle and to the geometry of circles or triangles is not at all visible here on the surface. This is quite a deep connection between this algebraic expression and the geometry that motivates the definitions of sine and cosine. So there's a lot going on here. And so computing partial sums of this series gives us an effective way of approximating the value of sine x for any real number x. And again, if you have time on your hands and you feel like experimenting with this, it's quite an interesting kind of experiment to just sort of calculate a few terms of this series for some value of x and compare it to the value that your calculator or computer gives you for the sign of that particular number. Okay, so an exercise which I think is a good one to do if you're thinking about Maclaurin series representations is to just calculate do the corresponding exercise for cosine. Just calculate the Maclaurin series for cosine x. And what you find there is that the terms that appear are the even order ones. So the even powers of x appear there, not the odd ones. And this is the expression. So it's basically, you get 1, which is cosine of 0. You get minus 1/2 x squared. Sorry, 1 over, yeah, 1 over. Sorry, I won't write this down. I don't want to write it down wrong in the last couple of minutes. But essentially, it resembles the series that we have for, yeah, it is 1 minus 1/2 x, 1 over 2 factorial x squared. You get all the even terms appearing, so you get plus x to the 4th over 4 factorial and so on. So you get something that resembles very much the version for sine, except that it's the even powers of x that appear, not the odd powers. And indeed, cosine is an even function. Too surprised about that. And another observation that you can make, although I don't recommend this as a way of calculating the Maclaurin series in the first instance, is that if you actually take the Maclaurin series representation of sine x and differentiate it term by term, you in fact get exactly the Maclaurin series for cosine x. So these Maclaurin series, they even sort of respect what we know about derivatives, that the derivative of the series for sine should be the series for cosine, and so on. So that's the concept of a Maclaurin series. It's a special case of what's known as a Taylor series. And basically the difference is, if for a Maclaurin series, we're always kind of working about 0 and we're evaluating our function at 0. One can adapt this relatively straightforwardly to use some other point other than 0 as kind of the focal point and to work around that. And if you do that, you've got a Taylor series. So a Maclaurin series is a Taylor series that's specific to the point 0. It's a sort of a special case of the Taylor series, which appears in Taylor's theorem. So that's as much as we're going to say for the moment about power series representations. You'll certainly meet them again in the future if you persist with mathematics, as I hope you will, and I hope we'll see you very soon here in person. There's a wealth of information. There's a sort of wealth of knowledge on this subject, which is fascinating and interesting, but that's where we're going to leave it for now. And other good examples. There are a few more examples in the lecture notes. Another good one to do is the exponential function and various other trigonometric and exponential functions. So I suppose after this section, what I hope you'll be able to do is to explain what a power series is, explain the concept of the radius of convergence for a power series, maybe with that example of 1 over 1 minus x, and for a given function that can be evaluated at 0 and whose derivatives can be evaluated at 0, to calculate some coefficients of the Maclaurin series. So I won't ask you for a detailed exposition of the theory behind the Maclaurin series or to explain where the formula comes from the coefficients, but I might ask you to do a few coefficients in an example just to show how the formula works. So it'll be a sort of fairly practically oriented kind of question like that. So, okay, I have exceeded my time. Apologies for that. Thank you very much, everybody. I'm going to stop the recording now. So thank you very much to everyone who joined us for the recording, and see you tomorrow.